Thank you very much for the introduction. Thanks for the invitation and the opportunity to speak here about frontiers of sphere recognition in practice. So this is a joint project with Frank, who we celebrate today, and his two PhD students, Davide Lofano and Mimi Tsuruga. And so this is a project which went on for quite a while, and I will tell you something on the way. I will also try to mention a few things to the left and to the side of the path, which are related to Frank's work. All right, so that's the plan. I want to talk about the problem. So you have a topological space given as a finite abstract simplicial complex, and you want to decide, is this a sphere, yes or no? There are a couple of technical ramifications. There are tools on the way. So there's two key ingredients on the tool side. So one is discrete Morse theory. I'll say a few words about that. I'm sure that Bruno will say much more about it later. And then I will also talk about bistellar flips very shortly. So this is what you saw in Karim's talk. So that's why I think I'm in the middle. I'm making the transition from Karim to Bruno. And so the most important part is the report on the number of experiments to see to what extent this heuristic is useful. There's various kinds of input. And then you can try to find the limits of this heuristics. And then there is something about specific data, again related to Frank's work. All right, so let's start with heuristic sphere recognition. So what's the algorithmic problem? You have a finite simplicial complex given, let's say as the list of facets, and you want to ask, is this PL homeomorphic to the standard sphere, right? So in the sense that, so is there, so if you translate it to what Karim said, so you can also ask, is there a sequence of these bistellar moves from your simplicial complex to the boundary of the standard simplex? And so this problem is trivial if you ask this for low-dimensional spaces. So if you do this for the two-dimensional sphere or one-dimensional sphere, that's very easy. If you do this for in 3 dimensions, well, so there's already a host of research on this subject. And let me mention in particular work of Rubinstein and Thompson from the 90s, who came up with a procedure to decide this. And then there were several groups of authors working on more precise complexity questions. So Haas, Lagarius, and Pippinger, and later Saul Schleimer proved that this problem, this decision problem, is in NP. And later Haas and Cooperberg, Zentner, Leckenby, so they also showed that this is in co-NP. But interestingly, there is a condition under which this co-NP-ness has been proved. So this is the generalized Riemann hypothesis. This comes in through the existence of certain types of solutions to certain systems of polynomial equations, and then it's quite subtle. So, but none of this will play a role for the purpose of this talk. In dimension 4, the question is open. So we do not know if there is a decision procedure to do that. But in dimension 5 and higher, we know for sure that this can never work. Right? So what am I talking about? I'm talking about an algorithmic problem, which sounds very easy. Right? So you have a simplicial complex. You want to know, is this a sphere, yes or no? And then if you go to dimension 5 or higher, so this is impossible. So then maybe I should go home and then do something else. But the problem does not go away, right? So this actually occurs in practice, and the talk is all about, so what do we do nonetheless? And just as a comment, so like in Karim's talk, we are in the PL homeomorphic setting. So I'm not asking for abstract homeomorphisms between arbitrary topological spaces. I'm sticking to this PL world. I will also mention software implementations, and most important for this talk are 2. So one is Ben Burton's Regina, and then there's a project called Polymake. So this is something that Yevgeny Gavrilov and the team of co-authors and myself have been working on for the last few decades. And so our implementations have been done in Polymake, but we also use Regina. You will see this a little bit later. And then there's a third software system that you will see in a few minutes. All right, so this problem is very natural. It is super hard to the extent that in the algorithmic setting it's undecidable for high dimensions. So, but what are kind of things that can come to our aid to solve this problem nonetheless in situations where we are lucky? Okay, so, and the most important thing is a theorem of Whitehead. I here give it in the version of Robin Foreman, who invented discrete Morse theory. So this is something that I already mentioned. So in this version, we are talking about a combinatorial D-manifold. So we already make an assumption on the simplicial complex, which I will explain in a moment. And then suppose that there is a discrete Morse function, right? So this is a discrete analog of a continuous Morse function. In the continuous world, you try to understand topological spaces, let's say manifolds, by embedding them in a space that you know well, Euclidean space. And then you have a height function and you just look at how the manifold, the sublevel sets of the manifold change with respect to this height function. So this is continuous Morse theory or smooth Morse theory, and there's a combinatorial analog. I will give you a more technical description on the next slide. If you have a discrete Morse function with exactly two critical simplices, one in dimension 0 and one in the dimension of the space, then this is a certificate that the combinatorial manifold is a combinatorial D-sphere. So combinatorial manifold means, so this is reasonable in the PL setting, which means, well, if you want to be a manifold, what does it mean? Well, then every point must have a neighborhood which looks like a Euclidean space of the appropriate dimension, right? And so combinatorial manifold means you want to see this in the triangulation, which means that the links of vertices are embedded spheres. And equivalently, the stars are embedded balls. And this is the setting. I should say, and you will also see this in the talk. Yes, I'm phrasing most of this in terms of spheres, but just there's also the side story. So what about other manifolds? If you have a combinatorial manifold given, so can you decide if this is a projective space or some other space? And so these questions are very related, but so in a sense, the situation focusing on the sphere is the natural point of departure, but I will also talk about the other things as well. So let me, so I think most of you are familiar with the discrete Morse theory. Let me remind you nonetheless of the basic setting. So leaving the bulk of this to Bruno, but so in the version that I want to look at it here, it works as follows. So suppose you have a simplicial complex, K, and then you look at the Hasse diagram of the Facebook set. What is this? Right, so you take all the faces of all dimensions, right, and you turn these into the nodes of a directed graph, and you have directed edges whenever K face is contained in the K plus 1 face. You make a directed arc from the K face up to the K plus 1 face. So all my arrows are directed upwards with increasing dimension. Right? So this is how you start with a finite simplicial complex, and you get a finite directed graph, which is obviously acyclic because everything is just pointing upwards. Now, so what's a Morse matching in this thing? So, and this is in this, if you think about functions, right? So in the discrete Morse function world, you assign values to all the faces of K. Now this Morse matching is like an equivalence class of such Morse functions, and this is encoded as a subset of the edges of the graph that are defined before, right? So you have the simplicial complex, you go to this Hasse diagram, which is this directed graph. Now you pick some of the edges of these directed edges, And they need to satisfy two conditions in order to be eligible for our game here. First, they need to form a partial matching, which means in the set of edges that you pick, you're not allowed to use the same vertex, meaning face of the simplicial complex, twice. So this is what it means for a subset of edges of a graph to be a matching, not necessarily perfect, so partial matching. And the other condition is, well, we had this direction on these arcs. So in the beginning, everything was pointing upwards. Now you have this matching, you pick those edges, and in those edges you revert the orientation. And now one of two things happens. So either the graph remains acyclic, or you create an oriented cycle. And I hate oriented cycles. So if you don't have an oriented cycle, then and the graph remains acyclic, so then you have a Morse matching. Matching plus this acyclicity condition, and this is, so here you have an example. So this is a simplicial complex of dimension 2 with 6 vertices. Here are the 6 vertices, 15 edges, 10 two-dimensional faces. So this is just the 6 vertex triangulation of the real projective plane. And so you have the directed edges, and the bold edges are the ones in the Morse matching. It requires a moment to check that this is really acyclic, but if you do so, then you can interpret this on the simplicial complex. Now this is the triangulation of the projective plane, like half of an icosahedron. Right, so here this point is the same as this, so identification around the boundary. And then you have unmatched faces, so these are the yellow ones, a vertex, an edge, and a triangle. So this vertex, this edge, and this triangle. And then these edges in the matching kind of can be seen as inducing a flow on this manifold, which contains gluing information, how to produce CW complex worth describing this projective plane. So, right, so you know you can create a projective plane from with 1 0 cell, 1 1 cell, and 1 2 cell, and and then this is how you can get systematically. So this Morse matching describes how to start with the triangulation and how to produce this more efficient cell complex with the attaching maps in a systematic fashion. That's another way of seeing this. So, okay, so I'm in the world of kind of computational topology where I want to solve an algorithmic problem, and I already told you, well, this is hopeless because it's an undecidable problem. Then I said, okay, but we have a little bit of hope. We have Whitehead and we have Morse theory. Now there's another bummer here. So if you have a finite simplicial complex and you really want to find a good Morse function, then that's hard. So what does it mean to be good, right? So you saw this cell decomposition from the projective plane. You start out with this triangulation, which is inefficient in the sense that you need rather many cells to describe the projective plane. But with just 1 0 cell, 1 cell, and 1 2 cell, that is way more efficient. So, and these corresponded to the critical, to the unmatched faces of my Morse matching. Now, you would like to find efficient Morse matchings with as few critical cells as possible, and then unless P is equal to NP, you cannot have this in polynomial time. So this is what this this result says. Like many results, also this obviously depends on numerous work of other authors, and so which are used to build the various gadgets in this usual NP hardness proof that you see here. And later, so there's a more recent analysis which is more precise than what we did. So in the world of parametrized complexity, Burton, Lewiner, Pichau, and Spreer gave a very interesting interpretation of what is going on here and proved a stronger results than what we had. Okay, so this is discrete Morse theory, and now I can tell you a little bit how our heuristics works. So you put in a closed combinatorial D-manifold, so closed means no boundary, and let's say we are connected. Otherwise, Well, if you want to decide if this is a sphere and you start with something disconnected, well, you know immediately it cannot be a sphere. And so the dimension 2 or lower is the trivial case here, so it's safe to assume that the dimension is at least 3. So, and then the question is this now a combinatorial sphere? So that is this PL homeomorphic? So is there a sequence of bistellar moves down to the boundary of the standard simplex? Yes or no? And in the first thing that you can do is you just compute this Hasse diagram of the simplicial complex, and then we use this Whitehead Foreman trick, and so just assume you just guess a Morse function. Yeah, you produce such a matching at random, and then maybe you're lucky. And if you're lucky, so which means you have a Morse function with exactly 2 critical cells, well, then you have a certificate that you got a sphere. Okay, of course you cannot insist on being lucky, so you need to do something if this is unsuccessful. So you can compute the homology of the space, and maybe the homology does not fit, is not the homology of a sphere. Well, then obviously the space cannot be a sphere. And you can look at the fundamental group, so you can look at your triangulation, and you can turn the triangulation into presentation, finite presentation of the fundamental group, very classical work. And then if the fundamental group happens to be trivial, then you are also in good shape, because then you are in the situation that you have a combinatorial manifold which is simply connected, and then there are of course world famous theorems. So the Poincaré conjecture in dimension 3, proven by Perelman, just says if you have a 3 manifold which is simply connected, well, then it must be the sphere. And then we can return yes. And thanks to Smale, who solved the Poincaré conjecture in dimension 5 and above, so we can also do this in higher dimensions. And again, the only case which is open is the 4-dimensional case. That's kind of the most interesting here. And then what do? Well, we don't give up. So we just do these bistellar flips that Karim introduced and discussed, up to a point where we lose faith in the process. And but if we are lucky in the process, then we have another certificate of sphereness. There are 3 steps which I'm highlighting here in red. So these are the ones that I'm not going to talk about any further. Of course, I could. All these things have interesting stories to tell. So it is interesting to think about how exactly you want to compute this Hasse diagram. If you want to do this fast, if you want to do this naively, it's not very, very difficult. If you want to do this fast, it's worth thinking about. Computing homology, again, is standard. If you want to do this fast, it's worth thinking about. Computing fundamental groups, well, writing down the presentation is easy, but here's another undecidable problem, right? So this is, again, it's undecidable to take to check if a given finitely presented group is trivial or not. Okay, so but since we gave up bothering about undecidability on the first slide, it doesn't create any headaches now. Again, if you have a sequence of moves to simplify your group to the trivial group, well, then you're lucky, and so this is kind of which works to your advantage. So this is an idea which goes back to Frank and Bruno. You will hear more about this, and of course, in the end, well, if none of these things succeeds, either in the positive or in the negative, well, then you need to give up. What I should also say, so the order in which you do these things, so there are 3 kinds of gadgets, right? So there's the random discrete Morse part, there's the homology part, there's the fundamental group part. You can reorder this in any way you like, and depending on your specific input, it might look more promising to start with one or the other. But let's not get into the details too much. Here's again a reminder of this world of bistellar flips. So this is one of these flips where you just remove these 2 triangles in the middle, and you replace them by these two. It's a variation of what you've seen in Karim's talk. There are other moves where you add, increase, or decrease the number of vertices. Well, so the history of this topic is long and complicated. It goes back to Alexander and Newman, as you saw before, and so. But there's also important work of Partner on this subject, which establishes this theorem: two triangulations are homeomorphic if and only if there's a sequence of bistellar moves, but including the possibility of going up and down in Karim's picture. So historically, this was put to good use for the first time as far as I know, in the algorithmic part of topology. By Anders Björner and Frank, and so they use these to create a local search heuristics for sphere recognition and a few other things. So this is kind of this step here, right? So this step is Björner Lutz, and but they also use these random flipping business to produce interesting other stuff. So for instance, from this original paper, this is figure 4. So this is a triangulation of the Poincaré homology 3 sphere with this F vector. So 16 vertices, 106 edges, 180 triangles, and 90 tetrahedra. Right? So this is this historically important thing because Poincaré initially thought this was a construction of a triangulation of a sphere, and later it was found out that the fundamental group is not trivial, therefore it cannot be a sphere. So this is one of these objects which stood at the cradle of topology as we know it. And I already mentioned, so this is a picture from that paper. I think, so this is the typical, if you knew Frank, so you recognize his postscript handwriting. So this is the type of pictures that he loved. And I think this is maybe among his favorites. Okay. So, now, so suppose you have this heuristics implemented. So what can you do with it? I will give you several use cases, but here's the first one. So this is a type of thing that you can do at home if you're interested. So there's another piece of software that I didn't mention yet. So this is Oscar. So this is written in Julia. So this is a large collaborative project, mostly based in Germany, but with many international collaborators. So it is written in Julia, but it is not started from scratch. Instead, it just uses GAP for group theory and representation theory, polymake for polyhedral geometry, tropical geometry, and combinatorial topology, and singular for commutative algebra, algebraic geometry, and then there's a bunch of number theory. So the important thing is in Oscar, all these systems that you see here, GAP, polymake, and singular, are accessible with all their functions. So the full functionality of these things is part of Oscar, and much more. So here is how you can use it. Right? So it's a standard package. You just install it like any other Julia package. So you say using Oscar, then you're ready to go. Then you can type in things like this. So this is a construction which goes back to a paper of Casella and Kühnel from 2001. You just define a simplicial complex on the vertex set, in this case of 16 vertices, 1 up to 16, and you just write down the maximal faces, right? So sets of cardinality 5. Which means we're talking about a 4-dimensional thing. You only see the beginning of 288 of these faces altogether. Trust me, all of them have the same cardinality, so it's a pure complex of dimension 4 with 288 facets, 16 vertices, and then Casella and Kühnel in their paper, without the use of computer, proved that this is a triangulation of a known space. It is a K3 surface. So the K3 surfaces form a class of algebraic surfaces right? So over the complex numbers, therefore their real dimension is 4. And so in general, they may have singularities, but sometimes they are smooth. And if they are smooth, then they always share the same topology. So there are many algebraic surfaces, smooth surfaces, always sharing the same type. And the question is, does this simplicial complex describe the correct type, yes or no? Well, and then one of the things that you can do in OSCAR thanks to GAP is you can just write down, so you plug in the simplicial complex, you say, give me the fundamental group, so then it will just produce this finite presentation of this group. And then GAP can try to simplify the description. And here, this is so easy, it just tells you right away, well, this is the trivial group. And and then this is a certificate that the complex that you put in is simply connected. Right? So this was the first step. You know, it's already an illegal step, right? So it's something undecidable in general. But if you're lucky, okay, you're lucky, right? So then you can work with it, and it's you get a certificate that this is a simply connected space. And here now in this thing, it is, so this is, in all of this, this is the most complicated and most costly step. Still on your laptop it will work in a second or less. So this is just checking if this space is actually a manifold. Right? And it just does exactly what I announced previously. It goes through the 16 vertices, constructs all the vertex links, and checks that these are spheres by applying our heuristics. That's implemented in polymake, but since OSCAR knows polymake, so it can benefit from this thing. Right? So this is manifold is a 3-valued function. Right? It can return true, it can return false, or it can say, well, don't know. Right? So that's, but that's possible in Julia. All right. So then we are almost done, because you can compute the cohomology of this space, right? So it's a 4-dimensional space, so you have cohomology modules from rank 0 up to rank 4. So these are like this, right? So this is a complicated way of writing down the trivial group. And then you have, so you have 3 groups of rank 1, 0, 22, 0, and 1. And then once you have that, so there's a known famous result about the topology of 4 manifolds. So it's due to Friedman, right? So if you have a simply connected 4 manifold, so then you only need to compute the intersection form, which is just a condensed version of the cohomology multiplication, right? Because if you have this thing, if it's simply connected and Poincare duality, right? So by the condition having a 4 manifold which is oriented and simply connected, so 4 out of 5 of these cohomology modules are already defined. Right? So this is connectedness, simple connectedness, and then thanks to orientability, thanks to Poincare duality, this is defined too. And only this one is kind of left open. And then if you restrict the multiplication of the only non-trivial contribution to the cohomology multiplication is what happens if you take 2 co-cycles, multiply them to get a 4 co-cycle, right? So, and then, right, in general you have a multiplication in a cohomology ring is not commutative, almost, up to sign, right? But since this is in even dimension, there is no sign flip, so you actually have a bilinear form, right? So you have a bilinear form on the space of with 22 z to the 22. You take and then you just need to understand what this bilinear form is, and then bilinear forms over the integers are classified, and this just computes. This is an even form. Right, so if you have the quadratic form evaluated on vectors and itself, so you always get an even integer, and then you can treat this quadratic form as a real quadratic form, right? You have Sylvester's law of inertia, you compute eigenvalues, right? So you have positive eigenvalues and negative eigenvalues, and then in this case you have 3 positive and 19 negative eigenvalues, and this identifies the K3 surfaces thanks to Friedman. All right, so this is a full proof on then how a given simplicial complex is a manifold that you know and care about. And so the crucial step, so there's this beautiful theoretical work by Friedman and others, but so then the actual computationally hard step is the sphere recognition that we're talking about. Right, so this, so shortly after the Casella-Kühne paper, I gave a presentation on how to do this in Polymec, which is pretty much equivalent to this, and later Jonathan Speer in his PhD thesis did the same. Okay, now, we have this beautiful sphere recognition heuristics, and we saw one example, this K3 surface, where it turned out to be useful. Now let's do this a little bit more systematic, right? So let's look at spaces that we can construct and check how well this works. Now, okay, so how do you go about this? There's more than one way, therefore several slides. So here's one thing that you can do. So you can produce spaces where you know a priori that you have spheres, right? And how do you do this? Well, you go through convex geometry. Right? So you can just take the unit sphere in your favorite space, you pick points uniformly at random on that sphere, and then you take the convex hull. Right? So this is with probability 1, this will be a simplicial polytope, so all the facets on the boundary will be simplices, and then you just take these, this combinatorial structure, this gives you a simplicial complex, which is obviously homeomorphic to the sphere just because it's a boundary of a convex boundary. And so these are these polytopal spheres, and let's start in the first dimension where I'm interested. This is dimension 3, right? So this was the dimension where we have Rubinstein-Thompson. We have an actual decision procedure, which is kind of complicated, but our friends from the Regina project implemented this. So Regina does Rubinstein-Thompson. So as part of this function is 3-sphere. And here we are using Polymec. So this is, I told you, so the project was something which was going on for a while. So this is a computation which was done a few years ago with versions both of Polymec and Regina, which are now outdated. Doesn't matter too much, but both systems became better, but the overall behavior is pretty much the same. So the only parameter which is left here is here on the left-hand side. So this is the number of vertices. You produce 3 spheres with 1,000 vertices, 2,000, and so on, up to 100,000 vertices. And then you can, I told you, you can play with the various ways of simplifying these simplicial complexes. And if you just do this with these discrete Morse functions, right? So then this is the timings that you take on a terribly outdated machine with only 8 gigabytes of RAM. But so this works pretty well. So this shows just doing these bistellar moves alone. So this was the original idea of Björner and Frank. So this does not work nearly as well. And so these dashes just mean, so we took a cut at 1 hour of computation time. And so this just means, or a little bit above. So these things cannot be done within an hour on this hardware. And so in order to get some reliable numbers, we did each experiment 100 times, and you see average values here. And so these stars just mean, well, these computations were so large, we only did this 10 times each rather than 100 times. So, but there's another way of how you can do this. So there's another, these bistellar flips can be combined with another variation of a simplification scheme, edge contractions. I didn't explain the details, not so important. So the thing is, you can be nearly as good as with discrete Morse functions. But so here on this slide, so discrete Morse functions are the clear winner, right? So you saw this multi-step procedure for recognizing spheres, and for this kind of thing, you don't need anything else but discrete Morse functions. Okay, that's what this slide says. Now, this is the exact procedure due to Rubinstein and Thompson, and this is nowhere near competitive. Right, so this is, if you compare these numbers, so this is for 15,000 vertices, You cannot do this slower than 100,000 vertices with this method. All right. So this was the first experiment. Yeah, please.
So in this table, it's all timing results. So
yes.
they all gave the correct answer.
All of them give the correct answer. Yes. So okay. So the experiment was done here in the way you let it run until it finds a Morse function which certifies this, right? Which I mean, it's a biased experiment. We knew beforehand what we had. It is just one way of testing these heuristics. Of course, I fully agree. I hope that everybody agrees that it is not sufficient as an experiment to convince you that this is a good idea. It is just the first step. Okay. All right. So this is the one thing. Here's another thing which is already more interesting. Before I explain it, so this is about four-dimensional manifolds. And this comes from a known census, so from the Regina project. Regina is a beautiful piece of software written in C++ and Python, but also it comes with a bunch of data. And among these data, there's a census of four-dimensional manifolds that you can produce in a certain way. Now I need a moment to tell you about the difference between Regina and Polymake. My description, my way of describing topological spaces in the Polymake/Oscar world was solely restricted to finite simplicial complexes. Right? This is now not how Regina thinks about topological spaces. Yes?
What's a pentachorum?
Yeah, that's exactly what I'm in the middle of explaining. This refers to Regina's way of thinking about it. Right? So this is I mean, obviously, it is more, you can describe topological spaces more efficiently in terms of cell complexes. But then the trade-off is, well, so yes, simplicial complexes are terrible because you need many simplices to describe something interesting. But the catch is, the beautiful thing about simplicial complexes, if you see them as cell complexes, then the boundary maps are always trivial. So you don't need anything to describe the boundary maps because they are just like they behave in a standard simplex. Now, if you pass to more sophisticated descriptions in terms of cell decomplexes, then you may win because you need fewer cells. But the price to pay is you have more effort to describe the attaching maps. Okay, and so now this the point of view of Regina is the one which is standard in low-dimensional topology, and so they still insist on forming cell complexes where each cell has the structure of a simplex, but you allow for more crazy gluings. So in particular, it is allowed to glue two faces of tetrahedron to itself. Right? So this doesn't happen for an abstract simplicial complex, but you can create meaningful cell complexes in this way. And so these are these pentachora. So these pentachora, so these are simplices with 5 vertices. That's the penta, right? So because you want to produce 4-dimensional manifolds, and then you have certain ways of writing down which cell is attached to which one in which way. But it is still fairly combinatorial. It's more general. The attaching maps are more complicated than for abstract simplicial complexes. Therefore, you need fewer cells to describe something interesting. But there is an effort to describe this, but it's still doable in a combinatorial way. Let me not be so. In the literature, there are 100 things. Sometimes they are called pseudo-simplicial complexes, and there's this little bit of variety of what is allowed exactly for gluing or not. Okay, so. But okay, that's what I want to say about it. And so one of the things that Van Burton and friends did was just to write down, just check what kind of manifolds can you produce from 2 pentachora, 4, and 6. So for some combinatorial reason hidden that I'm sweeping under the rug, so you want to have even numbers for these things. So that's why 3 and 5 don't occur. So, and then it turns out, so via the way that they are allowed to be glued in their game, So you can take 2 of these tetrahedra and you can form 8 different cell decompositions of manifolds out of it. If you take 4, you have 784, and if you have 6, you have 440,000. All right. So, and by construction, so that's the beautiful thing. So all these things are manifolds directly. So there's not just random noise of funny complexes that no one cares about. All of them are manifolds. So this is what they already do. And these are, so the gluing is called a signature in this game. So this we have 2 pentachora and 8 signatures, and similarly for the other. So now we applied our heuristics to this thing. And we recognized that, so these are the numbers that we recognized. So 75% of these are 6 out of 8 are spheres, and the other ones are non-spheres, and it's easy to say what they are. And here in this case, the 642 are recognized as spheres. So our heuristics is pretty successful. More than 80% we recognize that these are spheres, and for these ones we recognize that these are not spheres, just because in these cases the homology does not match. And there are only 5 out of 700 which were left open, which we could not decide. So this heuristics had 3 different kinds of exits: a yes exit, a no exit, and a I don't know what exit. And only in 5 out of 784 times it arrived at I don't know. And these are the numbers for 6 pentachora. So this means via this simple heuristics, in 99.5% of the cases, you can recognize what kind of manifold you have. That's pretty good, I'd say. So there's a word, right? So if you want to work with this data from Regina and to turn it into data accessible to Plenary, you need to turn it into a simplicial complex. And you just do this in the naive way. You barycentrically subdivide twice, right? So you are in 4 space. Then you have, if you have a simple 4 simplex, barycentric subdivision has 5 factorial 120 maximal cells. You do this twice, so which means the complex blows up by a factor of 10,000 in this process. Still not a problem for this heuristics, right? So you started with only 6 cells, and then you have about 100,000 cells after the second barycentric subdivision, but that's not a big deal, so it works quite fast. All right, so this thing, now there are several ways how you can go about it. So Frank was Frank was really annoyed by this line. So he said, okay, we must do better, okay? So what do you do? You have a beautiful tool, works pretty well, but not perfectly. So then you find a student. Okay, that's the name of the student is Antonia Perez Cerezo Flor, and she started the master's thesis with Frank in 2003, shortly before untimely passed away, and the task was, well, for this master thesis was very easy, right? There's this last line of this table, solve the problem. Okay, that's the thing. So there are a couple of unidentified 4 manifolds, and so the homology is right. So now, what did she do? So she played with all the ingredients. The interesting thing is, right, so on the previous slide for the 3 manifolds, I told you everything can be done in discrete Morse theory. Here, not so. So a couple of these things are, so that part that can be done through Morse theory could not be improved, interestingly. So, but what could be improved was the heuristics for doing these bistellar flips. So there are various parameters to play with, and she did. And then you can have a newer version of Regina, and has more fancy ways of retriangulating this thing. And doing wild mixes of Polymake and Regina is what she did. And yes, we used some bigger hardware than a pocket calculator of a few years ago. Okay, and then with this, she was able to do much better. right? So in the 4 pentachora case, 5 triangulations out of 784 were left open, and now only 2 are left. So she killed 3 out of 5. And then for the 1949 triangulation of the 6 pentachora, so she identified everything except for 640. Right? So for the experts, right? So this situation in dimension 4 that occurred as a special case in this heuristics. It's known to most people in this audience, I guess, that this is a known hard case, right? So because of so there could be spheres which are homeomorphic to the standard sphere, but not diffeomorphic, right? So there could be a difference between the PL world and the classical topological world, and that we don't know. And people have been trying to construct exotic spheres. If you want to have a next shot at that ages-old problem, here are 640 friends of yours. Right? So these are the best candidates for searching for exotic spheres if you like to enter that game. But it's not easy to do that. All right. So, and then now I told you lots about success stories of our heuristics. Obviously, if you do this, you saw these undecidability things, right? So at some point, things must break. Where do they break? Okay, let me show you. I keep telling you, this is another running story here, right? So kind of dimension 4 is the most interesting case for most of these things. And here's a way. So you start out with a finitely presented group, says 2 generators, x and y, and you have these relations, right? So this one and this one. And then this is a known presentation of a group, which turns out to be trivial, but it is not trivial to show that this is the trivial group. And in our paper, so from 3 years ago, right, publishing process took a while, so we wrote it up probably like 5 years ago. So the paper says, well, GAP recognizes the trivial group for this thing, which depends on the parameter r, which is hidden here, in 25% of all tries for r equals 4, and is unsuccessful for any other value of r. Now I told you, so this is from a few years ago, new software versions come and go. Now that we have Oscar, right, so now you can do this instantly. I tried it up to r equals 20, so it's no big deal. On your laptop, in an instant, it will tell you this is the trivial group, there's progress. But so this particular group came up in work of Akbulut and Kirby, who wanted to construct exotic spheres, by the way. And so what they did was they took this thing and turned this into a handle-body decomposition of a manifold, right? So such that then this is the fundamental group. And they could, by construction, it is a simply connected space. So, and it was clear to them that these are homology spheres, right? So, but they did not know if these were actual spheres or not, and they were guessing, they were hoping to find exotic spheres. That hope was destroyed a little bit later by a work of Gompf and subsequently by Akbulut himself, who showed, well, these are standard spheres. But it's a non-trivial proof to see that these are non-trivial, non-standard spheres. And here's another contribution of Frank with his PhD student Mimi Tsuruga. So they came up with a triangulation of the handle-body decomposition. So starting with this handle-body decomposition, they produced a triangulation with these parameters, where R is this parameter R, and this is the vector. Now, if you take these spheres and throw them into our heuristics, well, that's the end of it. Right, so there is no way except for this fundamental group trick for the dimension 3 in which this works, but neither the random discrete Morse theory nor the bistellar flips work on these examples. So these are pretty bad examples. Okay, how much time do I have, by the way? I don't know exactly.
Because we started a quarter later, so you have still 13 minutes. Yeah.
13?
Yeah.
Okay, I don't need all, thank you, I don't need all the 13, but I need some. Okay, So now you can ask the questions, we have been dealing with dimension 3 and 4 all the time. What happens if you pass to higher dimensions? Let me not go into all the details. Again, just focusing on these discrete Morse functions, you can try to randomly collapse the simplex of various dimensions. You can do this very often, and then you can just check how often the greedy heuristics is successful or not. Right? So this is a way a random discrete Morse function on the simplex is the same as a collapsing strategy for the simplex. And then these are these numbers. And so you see up to dimension 13, or so there's absolutely no way that in some reasonable, unless you're super patient, to find a discrete Morse function, a collapsing strategy which fails. But then after a while, so these numbers increase quite steeply, and if you go to 25 dimensions, then in 92% of the cases, so the random discrete Morse theory will come to an end. So this is just a glimpse. Of course, one could do way more complicated analysis, but this is just a glimpse of what is going on in higher dimensions. And so this explains if you just stick to dimensions below 10, so then these things are super useful. Then there's another thing. So again, this is typically Frank, right? So now you have these experiments with these Morse functions, and in some cases, you get a discrete Morse function which is not successful, where the collapsing strategy doesn't collapse everything down to a point. So which means you get stuck in some subcomplex where you cannot continue. Frank said, okay, let's look at the subcomplexes. And so this is how they look in surprisingly many cases. So this was a construction that Frank was obsessed with, I can say. So this is if you're familiar with the standard Dunn set, which is a standard space which is known to be contractible but not collapsible. So these are like bigger brothers and sisters of the Dunn set. So he called them saw blade complexes for this picture. So they depend on a parameter. So it's a cell complex, and so they look like these saw blades here with 3 blades, and so they can be triangulated. And then, like the Dunn set, they're always contractible but never collapsible. And very often we found in the analysis of the previous thing that these things are the reason why you get stuck. So this pattern that you see here occurs surprisingly often. All right. Okay, so from all of this, you see, so Frank was a person much interested in computational experiments in topology. And so over the years, he came up with many interesting constructions, and he saw many interesting complexes. And at some point, he started to collect this. And this is his manifold page, which kind of still exists. And it is still kept by our institute. And so it has all kinds of things, surfaces, 3 manifolds, vertex transitive triangulation, and so on and so forth. But of course now, and then this is really useful. So these are combined results from dozens of papers with many co-authors and complete classifications of sorts of this and that. And this is really, it's a rich source for doing computational topology. And one of the things that we will do is we plan to rescue this now orphan data set to give you an idea of what we are looking at. So this is a typical thing. So all these, the actual data is in text files. Frank used GAP a lot, and also polymake. And then these are ways to describe simplicial complexes. This particular one comes from this collection of flat 3 manifolds. This is just the first entry, which is like the simplest flat 3 manifold, which is the 3-dimensional torus. Has a symbol, has an F vector, has a degree sequence, a couple of other combinatorial information, and this is the explicit list of facets. Right, and so there are all kinds, there are triangulations of manifolds with up to 10 vertices, and so on and so forth. So all of these are useful for people working in computational topology, and we want to make this available as a database. So this is a part of a larger endeavor of a research project in Germany, Mathematical Research Data Initiative, and with Anthony Della Vecchia from my group and Jonathan Spreer from the University of Sydney, we will take care of Frank's data and modernize this, such that you can access it through standard APIs, both from Polylake and Oscar, and maybe other software systems if they are interested. Okay, so this is now the end of my presentation. So I hope that I convinced you that sphere recognition, despite hopeless, is not so bad in practice in many cases. But of course, there are things that we can't do, and I gave you these explicit triangulations that came out of this construction by Hulud and Kirby, and then Frank with Mimi Tsuruga. And yes, we will take care of this data. And this is a photo that I took of Frank in Oberwolfach in 2015. So, thanks for your attention.